Welcome. In this tutorial, we will dissect wah-wah guitar pedal. Yes, the sweeping vocal-like guitar tone that you hear in songs like Voodoo Child, Sweet Child of Mine, Shaft Theme, White Room, etc. So let's get started. Let's first hear this effect and understand how it happens. This is without the guitar, without the wah effect, and now with effect. That sweeping vocal-like guitar tone you just heard, that's the legendary wah-wah effect. At its core, the wah-wah pedal is nothing but a bandpass filter whose center frequency continuously sweeps back and forth. The filter allows only a narrow band of frequencies to pass at a time, and this band moves creates the expressive wah sound we all love. So the next question is, how do we implement this filter in real life? Practically, if you see, a bandpass filter is implemented using RLC component, and if we make this R variable, which is what this pedal is used for, then we are able to sweep the center frequency of the bandpass filter. So in this section, we are going to build this effect from scratch, first in analog electronics and then in code. We will start by using an op-amp based gyrator to simulate an inductor, making our bandpass filter small and practical. And then we will take the exact same idea to Python, where we will simulate the wah-wah pedal digitally and even animate the filter sweep in real time. So buckle up, this tutorial will be perfect blend of music, math, and electronics. Welcome. In this section, we will understand how a bandpass filter works. We'll start with the basics. For example, RL circuit and RC circuit, and we'll try to understand why inductors are not preferred in audio circuits and what is the equivalent replacement for an inductor. So let's get started. As shown on the screen, I have a RL filter. My R is 1 kilo ohm, my inductor is 160 millihenry. And from the basics, we know that the impedance of inductor is given by the formula 2 pi FL. And when F is low, the entire impedance of the inductor is low. For example, for F is equal to 0, that is DC, the inductor acts as a short circuit. And when F starts to increase, the inductor tends to become an open circuit. So now when we look at this circuit, at lower frequencies, this inductor will act like a short circuit, and the entire voltage that is present at this point will get grounded, effectively meaning that low frequency signals will not be passed through to the output. But when the frequency starts to increase, the impedance of the inductor also starts to increase, and this inductor then starts to act like an open circuit. And since nothing is going down to the ground, everything which is coming from the input will be passed on as an output. So the formula for the cutoff frequency is given by R divided by 2 pi L, and in this case our R is 1000, that is 1K, and our inductor is 160 milliohms. So when we plug these numbers, we get a cutoff frequency of 1000 Hertz. So let's run this simulation and understand whether this whole theory is working or not. So I'm talking about this circuit, and I'm just putting my probe here. So on my x-axis, I have frequency going from 1 Hertz to almost 3 kilohertz. And on the y-axis, I have the power in dB. So let me put a cursor. So now you can see that at 1 kilohertz, my signal becomes 3 dB. So firstly, it's a high-pass filter. As you can see, all these lower frequencies are getting attenuated. And at 1 kilohertz, I can see that my power has dropped down to minus 3 dB. So this circuit indeed is working like a high-pass filter. Now our attempt here is, as I mentioned earlier in the tutorial, inductors are not preferred in audio circuits for various reasons. Firstly, their behavior is non-ideal. Secondly, they are bulky. Thirdly, they are costly. Fourthly, they have saturation-related issues. So we have to find some way to replace this inductor with an equivalent circuit. So what can that be? So I then make another circuit with the hope that it will perform exactly the same way as the previous circuit is working. And this time it is made from a capacitor. So I have now chosen a capacitor here, 160 nanofarad, and a resistor. Resistor continues to be 1K. And from the basics, we know that the impedance formula for capacitor is 1 divided by 2 pi Fc. So when this F is very small, this entire expression becomes very large. The impedance becomes very large. That means at lower frequencies, the capacitor acts like an open circuit. And when this frequency starts to increase, then this impedance starts to decrease. And that means that for higher frequency, the capacitor acts like a short circuit. So let's see how it's behaving in this particular configuration. So when the frequencies are low, this capacitor blocks them and nothing passes on to the output, which means it's a blocker for low frequencies. But as and when the frequency starts to increase, this capacitor tends to act like a short circuit, so the signal starts flowing out, and the voltage that is appearing across this resistor finally finds its way to the output. This is working like a high-pass filter. And the formula for the cutoff frequency here is given by 1 divided by 2 pi RC. So when we plug these numbers, we again come back to the same frequency which was there earlier. The cutoff frequency continues to be 1 kilohertz. So let's simulate this and understand whether this is functioning correctly or not. So now I put my probe on the output of the RC filter and see what happens here. So not surprisingly, it matches exactly as the previous circuit, the RL circuit. It's a perfect match. So this is the output of the RL circuit, and this is the output of RC circuit. And as you can see, when I place the cursor here, at 1 kilohertz, the power drops to 3 dB. So hence FC is the cutoff frequency. So essentially, both these circuits are behaving exactly the same way, but the advantage here in the second circuit is that we have gotten rid of this inductor. So now let's take it one step further. The idea here is that I want this entire inductor resistor combination to be mimicked by an operational amplifier using resistors and capacitors. Let's come to a third circuit as shown on the screen. It's made out of op-amp and capacitors and resistors. And this circuit is actually called as a gyrator, and it acts like a perfect inductor. So if you see carefully, if you see the non-inverting input to the op-amp, it is exactly the same as the RC filter. In fact, component values are also just the same. 160 nanofarad, 160 nanofarad, 1K, 1K, and the configuration is also exactly the same. Also, please note that I have given plus minus 12 volt power supply to this op-amp to power it up. Now let's have a look at the input to the inverting end of the op-amp. Now this is directly short circuit with the output. So that's one point to note. So signal has two paths to travel. One is through this capacitor, and then through this this particular arm, the signal can travel. So let's analyze how this circuit is working. So let's start with the low frequencies. So when the signal is having low frequencies here, so both the arms get low frequencies, and we know that capacitor blocks the low frequencies. It acts as a blocker to low frequencies, so nothing passes through. And essentially speaking, at this point actually is grounded through this resistor, and the voltage here for low frequencies will be 0. So as we know from basic op-amp theory, whatever is the voltage at the non-inverting terminal, the op-amp tries to get exactly the same voltage on the inverting input. So if this is grounded, this will also act as a ground. And since this is ground, the output is also connected to this, so this also acts as a ground. So essentially speaking, what is happening? For lower frequencies, this arm is acting like a RL arm. If you see this circuit, for lower frequencies, this inductor acts like a short circuit. So nothing passes through the output. Exactly the same thing is happening here. For low frequencies, this node becomes 0, and since this becomes 0 or grounded, the output also becomes 0. Let's take the other case. In the other case, when the frequencies are high, capacitor passes them through, and the voltage drop appears across this particular resistor. Now, as per basic op-amp theory, this voltage must also get reflected at the input terminal. So this input then is equal to whatever that is coming from this side, and this forces the output to rise, which means the higher frequencies are being passed through this above arm. And again, it is mimicking the RL circuit as shown earlier. So for higher frequencies, this inductor acts like an open circuit. So for higher frequencies, since nothing can go to the ground, everything is passed on to the output. So this particular circuit called gyrator is actually acting like a combination of a resistor and an inductor. And the equivalent inductor value is basically multiplication between these three components, that is R4, R3, and C2. So when we multiply all these three together, so 1K multiplied by 160 nanofarad, this is what is written here, it becomes 160 millihenry. And since it's 160 millihenry, it is mimicking exactly the same inductance as is there in the RL circuit. Now don't pay too much attention to the units, because the units here will be ohm into nanofarads, and you will ask why it has become millihenry. Just ignore the units. But what is more important to know is that this R4 acts as R equivalent, which is 1K, and this combination, this multiplication of these three components acts like a inductor, and when you multiply them together, it is 160 millihenry. So since this entire circuit is acting as a RL circuit, and this RL circuit is exactly in the same value as this particular RL circuit, it should mimic exactly the same behavior as we have seen earlier. So let's run the simulation once more and see whether it is performing. So I had V out, which was exactly at 1 kilohertz cutoff frequency. Then I had, this V out 1 was RL, V out 2 was RC, and now I put my probe here and check the output 3, that is output of the gyrator, and no wonder, it is exactly matching the previous two circuits, and hence it is proven that this is acting like a RL inductor. If I place my trace here, so you can see that all three are at minus 3 dB when 1 kilohertz frequency is passed. So what have we done? The essential of this tutorial is that we wanted to get rid of inductors, and we have been able to do so by making a gyrator here and then effectively mimicking the behavior of an inductor. Now we will take this forward, and using this gyrator, we will make a band pass filter which is generally made out of R, L and C components, where L will get replaced with this gyrator. So see you in the next section. Shown on the screen is a RLC band pass filter. It comprises of three components: L, which is 253 millihenry, R, which is 100 ohms, and capacitor, which is 100 nanofarad. The center frequency of this filter is defined by the formula shown on the screen, which is 1 divided by 2 pi square root of L and C. So when we plug all these values here, we come to a center frequency of 1000 hertz. There's another thing that there's another characteristic of filter called quality factor, which decides how tight this filter is, how spiky the response of this filter is. So Q is defined by the center frequency divided by the bandwidth of the filter, and it's governed by the formula 1 by R multiplied by square root of L by C. So when we plug these numbers, we get a quality factor of 16, which is very high, which means the filter's response will be very, very spiky, and at this frequency, that is 1000 hertz, there's going to be a big resonance in the filter. So let's run this simulation and see whether this is indeed working or not. So as you can see, let me just rerun this trace again. So if I put a probe here and I disable the phase plot, you can see that there's a very sharp peak at 1 kilohertz. So at 1 kilohertz, the magnitude is 24 dB, which you can see is a very, very peaky response at 1 kilohertz. If I move left or right, this will start, the gain will start to reduce, as you can see here. So this is how a traditional band pass filter is made using RLC components. Now again, we come back to our previous argument that we would like to avoid inductors in the circuit. And the core idea is that if we can replace this L with a gyrator. But before we do that, let's make this filter center frequency steerable. What I mean to say is that let's make it let's make the center frequency variable, and to do that we can actually vary the inductance here. So let's give it a shot. I'll just copy this filter here and change its output to output 5. And what I want to do is that I want to convert this inductor into a variable inductor. So how this is done in LT-Spice is like this. I will call this variable inductor as L coil. So now it's L coil, and I will give a LT-Spice directive called declaring this as a parameter. So my L coil is a parameter, and C is small, and let's say it is equal to about 300 millihenry. So this is one directive that I want to put. And now I want this parameter to vary in steps. So there's another directive for that. So I want to vary my L coil parameter starting from say, let's say 10 millihenry going up to 300 millihenry in steps of say 10 millihenry. So this is another directive, and let's see what happens when I run this. So it's running the simulation, as you can see here. I don't want my previous trace, that is out 4. I'm interested in what is happening here. Brilliant. So you can see that by changing the inductance, the center frequency of the coil gets shifted. And this is exactly what a wah pedal does. The center frequency of the band pass filter is swept in the audio range so that it creates that swish kind of sound when wah pedal is pressed. So we are very clear that we are going in the right direction, and what is required to be done now is to somehow convert this traditional RLC based band pass filter into a gyrator based one. That will be in the next section. It's time to do a quick recap. We started off with a RL filter, and we proved that this filter's functionality can be mimicked by a RC filter. And then we went on and combined both these filters together into a gyrator, and we proved that a gyrator actually can replace inductor. Then we went on to make a traditional RLC based bandpass filter, and now in this section we are going to replace this inductor here with this gyrator. So let's start. Now in this section I have made this gyrator based bandpass filter. Let's have a closer look. Actually, if you see this circuit here, this is nothing but gyrator. It is a direct copy of this circuit, though I've changed the values of resistor and capacitor to suit the wah pedal design. But in structure, this entire thing is nothing but gyrator, and its equivalent circuit is shown on top. So this particular gyrator is a combination of a resistor, that is 50 ohm resistor, and in combination with op amp and these capacitors C5 and R8 potentiometer, it acts like an inductor. Now I have specifically chosen R8 to be a potentiometer so that I can vary the inductor. By varying this resistor, as you see that resistor R8 is in the denominator of center frequency. So if I vary R8, the center frequency will change, and that's what is the idea. Wah pedal changes the center frequency of the band pass filter, and this is how we are going to do it here. So on top, I've shown you this equivalent circuit which this gyrator is implementing. So we have L, we have R, and then I have introduced this capacitor 0.47 microfarad as C. So this entire section is nothing but acting like a RLC bandpass filter with variable center frequency. Variable because this R8 is variable here. This R8 is varying from 100 ohm to 100 kilo ohm in the steps of about 500 ohms. And yeah. So now the next stage, this stage is nothing, it's just a buffer stage. So what I've done is I've attached my guitar's input to the non-inverting part of this amplifier, of this buffer, and I'm simply buffering this signal coming out of this RLC filter, gyrator filter or bandpass filter, and just buffering it and then providing it to a load. Remember, since it's a resonant filter, the gain of this filter at resonant frequencies is going to be very, very high, and that's the reason I actually am giving only 10 millivolt signal to this filter. Otherwise, this op amp will saturate, it will hit the signal will hit the power rails and the circuit will become unstable. So the center frequency is decided by this formula here, which is again coming from the center frequency of a gyrator. And as I said, I'm varying R8 from 100 ohms to 100 kilo ohms. So the center frequency, if you plug all these numbers here, the center frequency is going to vary from 150 hertz to 2 kilohertz. And why this frequency range has been chosen? Because in guitar, the lowest note is open E string, which vibrates at around 84 hertz, and the highest note is again 24th fret on the first E string, that approximately vibrates at 1.2 kilohertz. So we are covering the entire guitar's spectrum, and this filter is going to be changing its frequencies between from 150 hertz to almost 2 kilohertz, covering the entire guitar spectrum. And hence these frequency components have been chosen accordingly. So let me run this filter. Actually, I've run this filter because the simulation takes some time. I'm just going to show you the results. So my output is at, let me just, so my guitar input is going to this amp and the output is coming from here, and this part is acting as a band pass filter. So let me just check what is the output. And here you can see I have a filter whose a band pass filter whose center frequency is changing depending on whatever is the value of resistor here, and it is going from as low as 150 hertz to almost 2 kilohertz. And this is what is exactly done by wah pedal, and this is basically the backbone. This circuit is the backbone of a wah pedal. Next, we will implement this in Python code.